Hi, my name is dr. Ahmath. In this video lecture, we are going to talk about linear equations. From this video, we're going to start a sequence of video lectures about a system of linear equations. So, especially in this video, we're going to talk about the definitions, the notations of the linear equations, and also we're going to define a system of linear equations and are going to discuss about the solutions of the system of linear equations. So first of all, I need to mention that a system of linear equations or just the linear equations have applied in many areas in our life, in biology, business, chemistry, or in the computer science. So throughout this lecture, we're going to see a couple of applications of the system of linear equations as well. But today, we're going to talk about the notation and the definitions of the linear equations. So you probably have seen the linear equations previously when we defined the equations of the lines or the planes. So if you remember, the equation of the line has been defined as ax plus by is equal to the c. So you may probably have seen this equation in a slightly different form, so which is expressed as the y is equal to the kx plus b form, right? But essentially, this two form of a line are interchangeable. So you can define the line using this equation or this equation. So later on, we've seen an example of the equation of a plane, also using a linear equation where we used to have like ax plus by plus cz is equal to zd. So this is the equation of a plane. So equation of a plane. So you see, so these two equations are the linear equations, and we need the equations in order to know what. So for example, if we are given a line using this equation, ax plus by plus is equal to the c, we know whether a point is on the line or not, or how to reach a certain point on that line. For example, if you choose a point with the coordinates x and y, then the x and y coordinate of this point should satisfy this equation. Basically, if I substitute this to here, I can find, I can identify whether this point is on the line or not. At the same time, if, for example, you're just given an x variable of this point, you can just substitute this x to this equation and can figure out what is the y coordinate of this point. So basically, you can know how to reach a certain point on the line. So this is essentially the same for the plane. So if in the plane you're given a some point, uh, P with the two coordinates, for example, x and y, you can just substitute the x and y to this equation of a plane to here and figure out the z coordinates. Or if you would like to check whether a point is on the plane, you can just substitute the coordinates of a point into the equation of the plane and figure out, identify whether this point is on the plane or not. So it's really important for us to define what we are going to call as a solution of a system or of a linear equation. So we say that, hey, the solution of a linear equation is going to be a vector, right? So in the case of a line, this is going to be some point, for example, is going to be a solution of a line, or in this case, it's going to be this point, which is going to be a solution of a plane. So there are infinitely many solutions if you're just given an equation of a plane or the line. So in general, we are going to define the equation of a linear equation in an n-dimensional space in the following form. So we're going to write this down as a11x1 plus a12x2 plus and so on plus a1 n xn is equal to the b1. So this is going to be the general equation. So general linear equation, a general linear equation. So please note that those numbers, a11, a12, and so on, a1n, are going to be just the real numbers. So a1n are the real numbers, including b1 as well. Okay, so on the right-hand side part, we usually have a free coefficient. This is free because it doesn't depend on the variables. Okay, and the solution for this linear equation, the solution is a vector with the n rows, For example, I'm going to denote the solution with the x vector, for example, and it's going to contain the n rows, and those components are going to be, for example, the s1, s2, and so on, Sn. And if this vector x is the solution for the system, it means that if I just substitute its components to this equation, the left-hand side should be equal to the right-hand side. So essentially, like A11S1 plus A12S2 plus and so on plus A1N Sn is equal to B1. Okay, so this is going to be called as a solution of a system. So, whenever we're going to talk about the system of linear equations, so system of linear equations, it is essentially just a bunch of linear equations which are given um, under the curly brackets. For example, we might be given as x plus y plus z is equal to the 3, and 2x plus y plus 3z is equal to the 1 is going to be a system of linear equations. So again, those equations are called linear because so for all the variables, the maximum power which is involved is equal to the 1. And whenever we say now, and this is the system now because they are going to have a common solution. So we will have common solutions. What does it mean? It means that if you've got a vector x, which is going to be a solution for one of the equations, it should be a solution for the second equation itself, as well, sorry. So for example, if you choose the solution, for example, like a 0, 4, and -1, if you substitute this to the first equation or to the second equation, it should be satisfied. So let's try to do this. So let me substitute this to both of the equations. If I substitute this to the first equation, so I need to substitute x to be equal to the 0, y to be equal to the 4, and z to be equal to the -1. So it's going to be 0 plus 4 minus 1 is equal to the 3. So it works for the first equation. And I can just substitute this to the second one. It is going to be 2 times 0 plus 4 plus 3 times -1. It is again equal to the 1. So it works for the second equations as well. So if you found a vector which is going to satisfy all the equations in a system of linear equations, then in this case, it is going to be called as the solution of the system. Okay, so and sometimes we're not going to have a solution for the system. Okay, so we are going to discuss this in a moment. In this case, we call a system as inconsistent. So basically, a system which has a solution is called a consistent system. Consistent. And a system without any solutions is called as inconsistent. Inconsistent. So later on, we're going to talk about the applications of a system of linear equations, and also we're going to go a little bit deeper about the consistency or inconsistency of a system of linear equations. But now we are going to discuss about what are the scenarios on the number of the equations, a number of the solutions. So scenarios on the number of solutions. So it doesn't matter what kind of system of linear equations you're given, there are always three possible scenarios. So basically, let's assume that in general, a system of linear equations is going to be given as a11x1 plus a12x2 plus and so on plus a1n xn is equal to the b1 and so on, lots of equations. So let's say we've got m equations. Then it's going to be am1 x1 plus am2 x2 plus and so on plus am n xn is equal to the b. So this is the system of the equations. So no matter what is the number of the equations or number of the variables, there are always three possible scenarios on the number of the solutions. So it is possible that the system has unique solution. It means that we've got just one vector, basically one vector s, or so let's just denote this s. So with the components s1 and so on sn, and if I just substitute them instead of x1 and so on xm variables, then this is going to satisfy for all the equations. And there is only one vector which is exist. Okay, so in this case we call this as a unique solution. So it is possible that so the system has no solutions. There is no solution. Okay, and the third scenario is when we're going to have infinitely many solutions. Infinitely many solutions. Okay, so I would like to talk with you a little bit more about the lines. So let's say we are given just the system of linear equations with the two variables. So in this case, it's going to be system of lines, and try to figure out geometrically what would that mean? A unique solution, having unique solution, or having no solution, or infinitely many solutions. So in order to do this, I would like to draw a couple of systems. So a system or an equation with two variables is a line, right? So we are going to consider the system of linear equations with the two variables. So let's start from the first case when we're going to have a unique solution. Unique solution. So let's say we're given the equation like x minus y is equal to the 1 and x plus y is equal to the 3. Okay, so I need to mention that the system has a unique solution, and in order to illustrate this, I would like to draw both of these equations, and I'm going to do this using so-called GeoGebra application. So the first equation is x minus y is equal to the 1, right? So this is going to be a line, and the second equation is x plus y is equal to the 3. So well, I've got these two equations, right? So the first equation has the two variables, so that is why it's a line. And the second equation, so okay, so let me input both of these equations one more time. So x minus y is equal to 1, x plus y is equal to 3. So sometimes it might be invisible. So let's say again, so I've got two equations, two linear equations, and if I put them on the system, it means that I'm looking for a point which is going to be on both of this line. So this is what does it mean, the solution of the system. And then this point is going to be on the intersection of these two lines, and it's going to have the coordinates 2 and 1, and this is going to be the solution for the system. So let me write this. So the solution for this system is going to be some vector s, which is going to be equal to 2 and 1. And geometrically, it basically means that I'm looking for the intersection point of the two lines, right? So I've got this system, this line, and I've got the another line, and this point on the intersection is going to be the solution for the system. It is essentially a point which lies in both of the lines at the same time. So now, when we are discussing about the scenario with no solution, so it was no solution. So can you guess what kind of what kind of equations we might have where there is no solution? What does it mean? It means that there are no points, and so it, it doesn't simply exist a point which is going to lie in both of the lines at the same time, right? So in this case, I will get a line like this, for example, and the line like this, where they are kind of parallel lines without intersection points. So let me draw them as well. So if I would like to draw the two other lines, so for example, x plus 4, x plus y is equal to 4, and the second line is going to be x plus y is equal to 2. Okay, so in this case, I've got two lines again without any intersection. It means that there is no solution for the system of linear equations. Okay, so please note that to the form of this equation, so I'm going to rewrite those equations again. So here, so I've got first equation as x plus y is equal to the 4, and the second equation is x plus y is equal to the 2, right? So I've got x plus y is equal to one constant, but at the same time, x plus y is equal to another constant, and yeah, so it's kind of natural that it doesn't have a solution, but later on we're going to talk about a little bit more details on when the system has a solution or when it doesn't have a solution. Okay, so one thing which you can notice here is that if you would get a matrix with the coefficients of the system, then the determinant of this matrix would be equal to the 0, right? So this is just what I've noticed here. So but it doesn't mean that your system has no solution. So hold on, because we are going to consider the last case. So when we're going to have infinitely many solutions, infinitely many solutions. So in this case, let's say I've got two equations in the form of minus 6x plus 2y is equal to the minus 8. At the same time, 3x minus y is equal to the 4. Okay, so if I would like to draw both of these equations, so using an application again, so try to understand in which situation we're going to have infinitely many solutions. So I'm going to just say hide them. So let me write, it's going to be minus 6x plus 2y is equal to minus 8. And the second case is 3x minus y is equal to the 4. Nice. So do you see the green line? No, because it's on the on the bottom of the blue one, right? Again, so if I just hide the blue one, you're going to see the green one. So both of these lines are essentially the same lines geometrically. So they are the same lines. So all the points basically in one of the lines are going to be the solution to the system, right? Because they are going to be in both of the lines at the same time. So this essentially both of the lines are the same. So in this case, we're going to have infinitely many solutions. And again, so we can express all of the solutions, infinitely many solutions, and we can express those infinitely many solutions by or space of the solutions as describe a space of infinitely many solutions using a line again. So essentially, if I would be asked to just express all of those solutions just in one line, so then I would just write this in terms of the line. So we'll talk about this later on, but now here I just would like to, I just wanted to explain you that there are three scenarios, no matter what is the number of the equations and number of the variables. So always either a unique solution to the system, either there is no solution to the system, either there are infinite many solutions. It is impossible that your system is going to have two solutions, three solutions, and so on. So if it has two solutions, it means that it's going to have infinitely many solutions. Okay, so whenever we are going to deal with the three variables, then it's going to be a little bit different, right? So for example, here, three variables means a linear equation with three variables. What would that mean? It means that we are given a system of planes. So a x plus by plus cz is equal to z is the plane, right? Essentially. So if you're given a system with three planes, then again there are three different scenarios. So either there is a unique solution, right? What does it mean? It means that you've got like a three planes, they're intersecting. So I'm just going to so draw those planes as a cross section on the z axis or yz axis. So let's say you've got three planes and they are intersecting in one single point. Okay, so in this case, this is going to be a unique solution. So again, those are the planes, not simply the lines, right? So I'm drawing the cross section of those planes. So at the same time, it is possible that you might have no solution, no solution. For example, in a case that all of your planes or just two of them are parallel, for example, like here, like this one. Yes, so it might be like this. So for example, the first plane, the second plane, and the third plane. So there might be points which are going to be on the intersection of two of them, but there is no point which is going to be on the intersection of the three planes at the same time. And whenever we're going to deal with the infinitely many solutions, solutions. So in this case, it is possible that your infinitely many solutions is going to be just the line or the plane. So what do I mean? So let's say you've got a plane as we discussed before, right? So just one equation, for example, ax plus by plus cz is equal to z. If you just multiply this equation to some constant, for example, 2ax plus 2by plus 2cz is equal to 2d, you're going to essentially have, again, the same equation or the same plane geometrically. So if you need to find the intersection points with another plane, for example, with this one, okay, then in this case, it's going to be a line, right? So here, the intersection points are all going to be on this line. And all of these points along this line are going to be the solution for the system, okay? So in this case, we're going to have infinitely many solutions, but it is possible that you're given a system with three planes which are essentially the same geometrically. In this case, those infinitely many solutions are going to be simply all the points in one of the planes. As we discussed this in a previous example, was the infinitely many solutions for the lines. So this is essentially what is the linear equations, what is the system of linear equations, and also the solutions for the system of linear equations. In our next lectures, we're going to try to discuss how to find the system, how to find the solutions for the systems in a more systematic way, using, for example, the matrices.